Hello everyone. Welcome to topic 3, Accelerated Data Science with GPU. In this topic, we will give an overview of data science acceleration with GPU. And we will talk about some basic and advanced concept of GPU acceleration. We will give a general introduction on an open source software library called Rapids, which give you the ability to execute end-to-end data science and analytics pipeline entirely on GPU. We will provide some examples on how to handle large dataset with QDF and how to accelerate machine learning with QML. Before we deep dive into the technical details of GPU accelerated data science and machine learning, let's take a look at the overview and some background information for this topic. GPUs, or graphics processing units, have been used for decades in the gaming industry and became more popular when Sony first used the term with reference to its PlayStation console. They have been essential for the fast rendering and processing of computer games, revolutionizing the experience for gamers as graphics became more and more detailed, nuanced, and realistic. While GPUs were designed to render graphics through rapid mathematical calculations, it is this high-performance processing that makes them appealing for data science. It enables AI to learn from images and sounds, using massive amount of image and sound input for these deep learning processes. GPUs power neural networks being trained at scale so that end users can enjoy image, video, and voice-based applications, as well as the recommendation engines so many of us use today, whether it is to find a good restaurant or our new favorite sneakers. Let's take a look at the history of data processing evolution. In 1990 to 2000, people are using data warehouse, where relational database management system and data warehouse technologies enable organizations to store and analyze growing volumes of data on high-performance computers, but at very high cost. Then from year 2005, distributed storage system was invented. When data processing first started, it was kind of this big revolution of Hadoop, and it just allowed people to use these commodity CPUs to really do scale computation. And it was this paradigm of reading from this, doing something, writing to this, and kind of iterating through that. And then Spark came around, and Spark said, you know what? If you can put all of that in memories and keep most of it in memories, the whole process, you get these massive speedups. And then also MapReduce was a difficult paradigm to use. And so the Spark was really focused on ease of use and making a lot simpler for people to do massive scale computation. And recently, from year 2016, GPU accelerated computing concept was emerged. GPU cores process tasks in parallel, which is far more efficient for computing intensive tasks than CPUs. So generally speaking, the trend is we have faster data access and less data movement. However, we still need more computing powers. Even with something like Spark, doing kind of aggregations on big data is already very challenging. There is a dataset called New York City taxi data, which is a huge dataset. And what we see is that we get CPU limited very quickly. And if you go to Google and search about this dataset, the big data processing, you can see that data scientists explain where the real bottleneck today in big data computing is in CPU. We try to push all of it there, and we are going to hit the limitation. And this is really kind of the motivation for what we are doing to accelerate data science with GPU. So, how can we do better? We wanted to focus on full data science workflows. If we only accelerate a part of it, we are basically hitting on those laws, where you can accelerate one part, you can accelerate a lot, and you are only gonna get a certain amount of speed up into the end. And we want it to be Pythonic, because data scientists love Python, and Python is growing really fast. We want to have a simple Pythonic interface where we can do it end to end. And we want to be performance as people expected from GPUs. In the initial stage of processing data using GPU, although GPU can do things orders of magnitude faster than their CPU counterparts, copying and converting data basically killed all the performance. So what we realized very quickly is that we needed to have standards. We needed to build a system, and this is GPU Analytics Initiative ecosystem, in a way where data could seamlessly go from CPU app to GPU app and staying on the GPU. Because memory copies are essentially like the bane of any type of performance. We basically went from early stages of GPU apps and data science of reading and writing to system memory to Rapids, which is an open source software library developed by NVIDIA. Here, we keep things on the GPU as long as possible. We have common formats, and it really allows us to have a much more accelerating ecosystem. Rapids was established in 2017 with the goal of accelerating end-to-end analytics and data science pipelines on GPUs, and created GPU data frame based on Apache Arrow data structures. The GPU data frame enabled the integration of GPU accelerated data processing and machine learning libraries without incurring typical serialization and deserialization penalties. Let's talk about the need for an end-to-end acceleration. GPU acceleration of classical machine learning algorithms, such as gradient boosting, has already become popular. However, previous efforts at GPU accelerating data science pipelines have focused on individual machine learning libraries and not other crucial interconnecting pieces of the pipeline. This creates a problem. Let's say your data pipeline has 3 steps: loading the data, cleaning the data and performing feature engineering, and finally training a machine learning model, a classifier. Firstly, we load the data into host memory. Then we perform ETL tasks, including data cleanup and feature engineering steps such as filtering, imputation, and generating new features. These steps today are largely done using the CPU. After that, we must convert the output of the feature engineering step into the internal memory format of the GPU accelerated machine learning libraries, and then move the data to GPU memories. Now, we run machine learning model training. We get a huge speed up on the training step. Finally, we move the data back to host memory and visualize or prepare for model deployments. In this case, copying and converting data operations introduce significant overhead due to serialization and deserialization operations. Therefore, RAPIDS addresses this issue by designing a columnar data structure called a GPU data frame, which implement the Apache Arrow columnar data formats on the GPU. The RAPID GPU data frame provides a pandas-like API that will be familiar to data scientists, so they can now build GPU accelerated workflows more easily. There is a RAPIDS example demonstrating a typical end-to-end ETL and machine learning workflow. This example trains a machine learning model to perform housing loan risk assessment using all of the loan data from the years 2000 to 2016 in the loan performance dataset, consisting of roughly 400 gigabytes of data in memories. The example loads the data into GPU memories using the RAPIDS CSV reader. The ETL in this example performs a number of operations, including extracting months and years from date-time fields, joins of multiple columns between data frames, and group by aggregations for feature engineering. The resulting feature data is then converted and used to train a gradient-boosted decision tree model on the GPU using extreme gradient boosting. This workflow runs end-to-end on a single NVIDIA DGX2 server with 16 GPUs, which is 10 times faster than 100 AWS instances. Comparing GPU to CPU performance 1-to-1, this equates to well over a 50 times speedup. RAPIDS can achieve speedup factors of 50 times or more on typical end-to-end data science workflows. RAPIDS use NVIDIA CUDA for high-performance GPU execution, exposing that GPU parallelism and high memory bandwidth through user-friendly Python interfaces. RAPIDS focuses on common data preparation tasks for analytics and data science, offering a powerful and familiar data frame API. This API integrates with a variety of machine learning algorithms without paying typical serialization costs, enabling acceleration for end-to-end pipelines. RAPIDS also includes support for multi-core, multi-GPU deployments, enabling scaling up and out on much larger dataset sizes. When we are going to use RAPIDS, we mainly interact with it using these high-level Python packages. The first one is called QDF. QDF is a GPU data frame library with a pandas-like API. QDF provides operation on data columns, including unary and binary operations, filters, joins, and group bys. And then we have QML. QML is a GPU accelerated libraries for machine learning algorithms, including singular value decomposition, principal component analysis, density-based spatial clusterings of application with noise.